Well, hello there, this is Mr. Doro. Today I'm going to be talking about density particle diagrams and talk about how we can know the relationship between mass and volume based on density. Hold on, here we go. Well, we're going to start out with one of the problems from our worksheet, and this is number 4A on worksheet 3. And so we have a mass versus volume graph right over here. And you can see we have substance A and substance B. You can tell that the slopes are different just by looking at them. This one has a steeper slope, which means that it has a greater mass for the same amount of volume than this one does, or a greater density. And so that's what we're going to be comparing today. The question says that we have a two-pan balance that we built. And this two-pan balance, if masses are equal on each side, then it should stay the same. But it wants to know what if you had equal masses of A and B, and then also wants to know if you had equal volumes of A and B in the two pans, and wanted us to explain that. So we're going to look at some student work on that and critique that. Well, this is a whiteboard that a group of students did, and I thought it was a pretty good whiteboard, and I asked if we could go over that. I think it's going to make some great discussion for us. So the first part said when we had equal masses, I definitely agree that it would be balanced because it's equal on each side. The mass is the same. The question I have is, would these be about the same size for A and B? Remember, A had a greater density, which means it has more mass for the same amount of volume than B does. And so if this was B on this side, and these are both the same size, which is volume is the amount of space that it takes up, then if they're both the same size, then A being the greater density should be weighting this down. So I think that the way we should draw this is this way. We should say that we have a little, if they're going to be balanced, and A has a greater density, then it has to have a smaller volume. And if B has a lower density, it has to have a larger volume. And we can put that to scale too, depending on what the ratio actually is. If the density was 3 times greater for A, then this B would be 3 times larger than A would be. And then so the second part said, well, what if we had equal volumes? Well, equal volumes, I thought this group did a great job of drawing particles in here. And so equal volumes would mean that they are the same size. And so they drew particles in there, and the particles usually represent the mass. And we do if the particles are the same size, then they're the same mass. This one over here has 6 particles in it, and this one over here only has 3 particles in it. And so if we look at that, I like that the volume, these are the same size, take up the same amount of space, and they know that there's going to be an imbalance in those two. But this one having the more particles should probably be down lower. So this should be instead drawn like this, with the 3 particles up on the top and the 6 particles, there's 6 there, trust me, and 3 particles right in there. Because the more particles, the more mass if they're the same size. And just to see if what we've just talked about makes sense, I'm just going to pick a volume on the graph and we're going to compare them. So if I pick 40 milliliters right here on that crooked line, then you could see that substance B would be about just over 20 grams that the mass would take up at 40 milliliters. And substance A would be 60 something, in between maybe 66 or so grams that takes up. So these are both the same volume. They both take up the same amount of space, but substance B is more or less massive than substance A is in that same amount of space. And then just the double check of the other one that we did, if we had the same mass on each side, and so I'm just going to pick a mass of 20 grams, then the volume for A would be, I did that a little crooked, but somewhere around 10 to 15 in there, just maybe 12. And then if we had 20 grams of B, then that would be about 42 or so milliliters. So obviously, B is going to be much bigger, and if we look at this, it goes from around 12 to 42, so almost 4 times as big that we would have to draw that. So now we're going to play a little game called which one has the highest density in the pairs that we're talking about. So if we look at this, this doesn't tell us the exact masses and it doesn't tell us the exact volume, so we just have to compare them. If we look at C and D, we can see that they're balanced because they're equal on an equal plane there. C is obviously has a greater volume and D has a lower volume. And so this must mean that D has the particles more tightly packed. It has the same amount of mass, more tightly packed. It has the same amount of mass, but in a smaller volume, which means that D is the winner here, if you call that the winner, of the highest density. When we look at A and B over here on the side, then we see that A has a smaller volume and it has a greater mass because it's pushed down lower. B has a larger volume and a lower mass, which means that A must be more tightly packed because the volume is smaller and the mass is greater. And so its mass to volume ratio must be greater. So A is the big winner on this one. Between E and F, we'll see what we can tell in that one. Obviously, this one has the E has the higher volume, but it also has a higher mass. F has a smaller volume, but also a smaller mass. So really we can't tell because we don't know how the scale is. We don't know how much the mass has changed. And these actually may even have the same density. And if you think about it, if this was a hunk of iron, a larger hunk of iron, and this was a hunk of iron, they would have the same density, but this one would be the greater mass because it is the greater volume. And so we're not sure on that one whether they're the same material or not and how the densities differ. But we look at G and H, and for G and H I tried to draw the same size here. If these are the same volume, and that's usually what we try to do for density, we put it to grams per milliliter so that we can compare it to the same type of volume or grams per centimeter cube. So if they're the same volume, this one is the most massive, and if that one is the most massive for the same volume, then that's going to be the highest density. Well then, what if we had two liquids that were separated, and we got a red liquid and a blue liquid? They're both 50 milliliters, and they are separated, and you can see how they ended up separating in this graduated cylinder. So I'm wondering if we can label these up here. This is a mass versus volume. If we can label one of them as A and one of them as B. And then I wonder what we can do down here and saying on the masses if they would be the same or if they would be different. So let's talk about this real quick here. So on this first one, we have the mass versus volume. This one has a lower density. So which one of these two has a lower density? Come on, which one? Right, the one that's on top right here that's floating, that's going to have a lower density, and so this one up here is going to be our B, and the higher density one, which is obviously the one with the greater slope, is going to be the one that's on bottom, and so that's going to be our A right up top. Okay, so then now we got to look at this balance here, the two-pan balance, and we got to figure out, well then, are they going to be equal? Are they going to be balanced with each other? Well, let's think about it. If they're both the same volume, which both of these are the same volume, then something has to be different about them, and it has to be the mass. Which one's more massive for the same volume? Which one? That's right. This one that's on the bottom is going to be the more massive, so we're going to have the blue one that's coming down here, and it is going to be on the bottom. And my colors, sorry that I put red on red over there, but that's the way it would end up looking. So finally, what does that tell us about particle arrangement? Well, if we look at aluminum, and we know that the density of aluminum is 2.7 grams per milliliter, water is 1 gram per milliliter, and the gas that we did from the density of a gas lab was right around 0.002 grams per milliliter, then we can talk about how these particles go in here. And so if we put these all on the same volume, and I'm assuming that I tried to draw these boxes the same volume, then we could do a ratio right here and set these all up and see how many particles each one would have. So what I started out with is I put 27 particles of aluminum in that little box, and this is like it's 2.7 grams per milliliter, so I just multiply by 10 to get 27. So in order to get this right then, for water, I'd have to multiply that by 10, and I'd get 10 particles. Going to do that right now. And there are my 10 particles of water. I did them a different color, but they're the same size particles, and you can see that they're more spread out. In order to get the gas then correctly, I'd have to multiply that by 10, which means I only need 0.02 of a particle. So I don't know if you can see it or not, but I did try to do about a 0.02 of one of the size of these particles, and you can see about the arrangement of the particles in the same volume that we have aluminum, which is a solid, water, which is a liquid at room temperature, and a gas, and you can see why the density plays a big part in the arrangement of the particles. So now I've written the number of particles down below, 27 particles versus 10 versus like 0.02. But there is another way possibly that we can think about this. And maybe it's not the number of particles, but maybe it's the size of those particles that change the mass. And so I've drawn down here underneath that we have a 27, instead of 27 particles, only 3 particles, but maybe they're 2.7 times the size of this one, which is only 1.0 times the size, and then maybe it's the same number of particles each time, and then this would be 0.002 times the size. What's the right answer? Well, time will tell. Hopefully this helps you out. Have a great day. Bye-bye.